All right, thank you very much, Derek and Brian, and Christina, and Amanda, and Abigail, and Kate. My name is Paul Wolf. If you don't know me, I'm the Living Lab Manager here at MIT, and I'm going to lead you through the speed talks, which are meant to be presentations to highlight the work of the Incubator Fund winners. So for the first time, we had a Sustainability Incubator Fund Award that was administered last year during the summer, and today we're going to hear about some of this work so that we can understand what's really possible when you use the campus as a test bed, and to maybe understand a little bit more about what the incubation idea is all about. So the Campus Sustainability Incubator Fund was a wonderful opportunity to promote campus as a test bed, and it was possible because of the support by Malcolm Strenberg. And we are very happy to share the results of this work. The way it worked was there was a whole criteria that was distributed, and teams had to have diverse constituencies. So you had students and faculty, you had operational folks, there was a requirement for robust methodology and a timeline so that you could measure the impacts over time on our campus in the day-to-day operations. The idea being we were trying to fill the gaps between our academic and operational departments. So I'd like to get started with our first award winner, Jeremy Gregory. I'd like to invite you up here to the stage. Jeremy is a research scientist with MIT's Civil and Engineering Department, and he's going to talk about green labs and glove recycling on our campus. So let's welcome Jeremy.
Thank you very much. I need a clicker here. Great. Glad to be here, and as Christine said, it was a perfect segue to the work that we're doing. We have a big team that's working on this, and hopefully there's a set of slides that are coming, or I just click it next. Okay, great, there we are. Here you can see the team, and I'm the messenger, but as you can see, it's a pretty diverse team. We got people from EHS, from a couple different labs on campus. Elsa Olivetti is the main PI on this. There's a few people who started it. But the whole idea is about trying to understand the impact of the disposable gloves that are used on campus. And as you can imagine, MIT uses and disposes of a lot of these disposable gloves, and they're for all kinds of different reasons. Primarily to keep people safe from all kinds of stuff that they're handling, and also to avoid contamination of different types of items. And so there were a couple people on campus, primarily graduate students and postdocs, who just, some of us have this like kind of visceral reaction to throwing things away, and wondered, is there an alternative, something else that we can do besides throwing them in the trash? And so this is showing some of the initial pilot project, some of the folks who are involved in collecting some of these disposable gloves and then actually recycling them. And that bin right there contains approximately about 50,000 gloves just in that one bin right there that were collected and are now being sent to a vendor who is recycling those. And so far in this pilot project, they've collected about 1.25 tons of gloves, and those are used in like different types of plastic lumber applications, like chairs or decks or things like that. And so that project's been going on since late 2016. And the whole idea behind this incubator project we had is trying to measure the environmental impacts of doing that recycling compared to alternatives of landfilling them or sending them to incineration for waste to energy. And we are interested in this because sometimes you never know basically what are those different impacts. What's the environmental footprint of actually doing the recycling? Is it better? So we're trying to do that. And we have a couple different ways we're doing this. Thanks. One is we're using a life cycle assessment approach, which is basically quantifying the environmental impacts of these different processes, including making the raw materials, then making the gloves, distributing them to different facilities, sending them to MIT, and then sending them to either landfill, waste to energy, or glove recycling. And then with that life cycle assessment, we quantify all those environmental impacts and then can use a variety of different metrics to be able to look at what those impacts are. So we have a couple different steps involved in this. One is what Christine already mentioned. We've worked closely with the procurement office, and we have a UROP who's been actually analyzing this. And a big thing we wanted to understand was basically how many gloves MIT buys in 1 year. And I'm gonna follow on the approach here of adding some quizzes here. So here's alternative A is 500,000 gloves, B is 1 million gloves, and C is 3 million. Those are your three choices. So how many people think A, 500,000 gloves a year? Individual gloves. Okay. B, 1 million. All right, or C, 3 million. Wow, you guys are it's not A, it's not B, it is C. 3 million gloves in 1 year. And that's kind of a ballpark because we, as Christine knows, there's a lot of different data sources, but we feel pretty good about this. So it's quite a bit. Some of the other things we found in analyzing this, almost 90% of the gloves purchased are nitrile, so that kind of helps us in doing our analyses. And we're also able to get data on what are some of the different sizes, because different sizes have different weights, so we need that as well. So most people are using large or medium sizes, as you can see. So the other thing that we're working on now is trying to collect some life cycle assessment data on these different processes. So in particular, as Christine mentioned, we have been able to use this data and then work with her procurement specialists to contact some of the vendors who were the top suppliers to MIT, and we're currently trying to ask them to see if we can work with them to get some data. And then the other thing, we're also working with the vendor who does the glove recycling to collect data on that environmental impact. And then our last step will basically be to calculate environmental impacts using that data that we get. So it's kind of a neat way to take this pilot project, which Office of Sustainability is also helping to support, and then use that at MIT here. We like data-driven decision-making to help us analyze this whole process and see where we can make improvements. So once again, thanks to the team for doing this, and that's it.
All right, thank you very much, Jeremy. Next, I'd like to invite Randa to the stage. Randa Gaddis is a sustainability project manager working in campus construction, and she was an integral part of the team that studied life cycle impacts and supporting sustainable building on campus. So Randa.
Hi, how are you guys? So I'm part of the team in campus construction who's supporting this effort that actually Jeremy, who just spoke, is on. He's one of the lead researchers on this effort. And the purpose is to find methodologies to support sustainable building planning and design decisions at MIT. So many of you know, we always say when we talk about sustainability, we need to look at things through a life cycle perspective, right? So there's many ways to reduce the impact, the environmental impact and cost along the life cycle of a building. We can look at, for example, materials production and methods there. We can look at the design and construction phase. We can look at the use phase. I'm not going to read because that's too much information, but and then we can also look at the end of life phase. In each one, there's methods that you can do, but in order to really understand which strategy to use, you really have to do a trade-off analysis between performance, life cycle impact, or environmental impact, and cost. So to do that, you do life cycle assessments. I think Jeremy just kind of talked a little bit about what it is. In industry, in the building world, life cycle assessments have limited scope. They typically focus on the early phases of the life cycle. And if you know anything about life cycle assessments, they measure multiple things. One of them, for example, is global warming potential, which is GHG emissions, which if you're looking at the life cycle of a building or a product and you ignore GHG emissions because you're not addressing the use phase, you're missing 95% of the carbon impact. So it's still limited in how it's used in buildings. So at the same time, when we think about buildings and how we design, typically, if you want to influence performance, you want to get in there early in the process. You want to make decisions up front about what kind of performance you want your building to have. And at that point, it's also easier and cheaper to include it. As time goes on in the design process, it gets more expensive. And it gets more difficult because things get more fixed. You can't change your performance goals later. It gets just more complicated. So one of the things, and another key component that is, that's I think a difficulty is there's a lot of uncertainty. We use a lot of assumptions early in the process. Right? You don't know enough about a building early in the process. You know a little bit about it. You've made some assumptions about potential systems you're going to use, but it's pretty high level. So when you think about life cycle assessments, they require a lot of data, a lot of information. And so typically what you want is you want the design to be further ahead so that you can actually collect that data. And however, what we're trying to do through this method is to move it earlier in the process and account for design uncertainty. So at MIT, we utilize industry best practices to integrate sustainability. At the same time, I think at the industry level, we lack a comprehensive approach to full life cycle assessments. And without kind of diminishing other things, buildings are not gloves, they're not cars, they're not computers. There's hundreds of thousands of players. So it's much more fragmented as an industry. So it's hard to collect and get all the data that you need. And there's many specialized skill sets to have a building. And there's many methods and tools across the entire life cycle. We're not talking just about building a building. We're talking about making products. That go into buildings. We're talking about the users. We're talking about how we get rid of materials. So along the entire life cycle, there's many things going on. So there's a real opportunity to figure out how to do this. So at the MIT Concrete Sustainability Hub, which Jeremy is one of the key players, or he's the executive director, right? And they work on streamlined whole building life cycle assessment. And they use a methodology called BAIA, Building Attribute to Impact Algorithm. And it's a process that also requires a lot of data, lots of models, meta models, you can name it. And what the purpose is, though, is it integrates what's called probability and sensitivity analysis with uncertainty analysis. And what you do is when a designer comes in the early decision-making process, what happens is you get a range of impacts for a system or for systems. And so you can start to compare that, and you can start to prioritize where those impacts are, and based on the system that the different systems you're considering. So what we're trying to do right now is, this has been looked at in terms of single-family residential and multifamily. And we're trying to scale it up to commercial scale residential, starting with residential construction, since we started with single family. So we're looking at Site 4 as our case study. We're starting with our integrated design process and trying to identify through the data that we have on campus when the key decisions are being made, what kind of information is available. We're also started initiated conversations with the architect to look at the tools that they have and they've used, as well as the data that's available with those tools throughout the process. And then, as a result of that, trying to figure out how this methodology can be better integrated into a larger scale building in the early design. Thank you.
All right, thank you, Rhonda. And then We also are going to hear from Kripa Varnesi. I'd like to invite Kripa to the stage. He's an associate professor for the MIT Department of Mechanical Engineering, and his project is water capture and the central utilities plant. Let's welcome Kripa.
All right. Thank you so much for having me here and for all the support from the Office of Sustainability. So our goal in this project has been about solving a key problem at the energy-water nexus. So if you look at power plants, they use a significant amount of water. Almost 39% of fresh water withdrawals are earmarked for power plants for their cooling needs. And that costs about $50 billion. The cost of water itself is about $50 billion a year globally, and with water scarcity growing, that's only going to increase. And there are other side effects such as regulatory issues with these plumes that you see that come out of these power plants. So the problem we are trying to solve is to capture, let me see if my mouse is not working here. To capture the plumes that are coming out of these power plants. And those plumes are essentially, almost like distilled water. So it's like fresh water that we are letting go waste. Let me talk about some numbers. A typical power plant, like a 600 megawatt combined cycle plant at 55% capacity rate would use as much water as 100,000 people would. And the cost of that water would be about, $7 per 1,000 gallons. This is a number that also, came through with our working with the folks at the cogen plant here at MIT, Seth and Patrick. So the idea is, if we capture that water, then there's a significant savings for the power plants, but also I think we can get that back to the municipalities in places where water is scarce. So the way these cooling towers work is you need to cool the condenser of the power plant. So you use either lake water or river water, or sometimes and those are called once-through systems. But in most cases, this changing to these cooling towers where you get water from the municipalities, or and then you basically do this. Let me see if I have a pointer here. But you spray this water, you get evaporative cooling, and then all that water, okay, great. Okay. And this water basically comes out as a plume, and then this vapor condenses because the ambient air is cold and then forms this plume. So the idea, and so you see that all that water that's going out, there's about, this is for that system, 2,000 gallons per minute. So we built a cooling tower in the lab, a mock cooling tower. And then to study the plume characteristics, it's consistent with what you see in real life. And then what happens is, because of this evaporation, the water gets very rich in minerals, so you have to also dispose of that. So there's a significant cost to that as well. So overall, that's why you get this number. And so our solution was, to somehow, so the plume that's coming out is tiny, tiny fog droplets. These are less than 10 microns in size. And so we created a charging electrode that charges these and is able to capture it. So without the electric fields on, you see the plume coming out, and with the field on, you see that the plume disappears. And then we are able to capture all that water that's escaping out. And you see that you can reuse it back in the cooling cycle, or you can, because now this water is more, it's a higher quality water, you can use it as a feed water for a boiler, or you can actually, sell it back to the municipalities as water for, that could be used where water is scarce. So given the time, I'll skip this, but I quickly want to show you. So these kinds of measures have been used in fog collection, in places like Chile and so on. The reason why these are very, very, very low efficiencies, they're less than 3%, because when you put a mesh and you have these droplets, they just go around the mesh and they don't get captured. Now with our electric fields, we create an external field that actually forces these streamlines of these droplets to, in fact, turn around. And so our capture efficiencies are actually greater than 1. So we're able to push the efficiency to 90 to 99%. So what does this mean? So this means 150 million gallons of water saved for a plant like that, and $1 million in savings. And our energy cost to run this is extremely small because we are very efficient in charging these droplets, and we don't use as much power. These are some slides showing you where we stand, because we want to really take this and make it and translate this into the outside world. So the total addressable market is itself like $17 billion. This is in the US is alone $6 billion. And so where the pilot really came in handy and actually was a very important part of this project was, we did all this stuff in the lab, and then, before we go out and translate it, people always ask this question of, okay, so does this work at scale? So here was a great opportunity where we could have an enormous impact on the footprint of the water footprint of the campus, and at the same time prove out a business case. And so working with the folks at the power plant here at MIT and the Office of Sustainability and all this support, we want to thank all these folks here who really helped us to get in there and let us work with the cooling towers in the cogen plant. Here are my students and the folks from the plant. So where are we? We developed the pilot, and then this is how that collector looks like. And then let me see. We've been doing some experiments in the garage in the power plant. With the meshes and trying to prove out this technology. So we hope to put this on the cooling towers in the summer and demonstrate this at scale. And there's already been significant traction. We won a number of awards, including many business competitions. And so to give you an update, the roadmap really is sometime in July. We are also going to be spinning this off and taking this out as a company. And I think. The Office of Sustainability's role here has been significant to really get us to this level. And I just want to close on one final note. So what does this mean? Right? This is not just savings for power plants. This can have a huge impact on water globally. And these are some numbers between Infinite Cooling, which is our company, collecting this water, and desalination. And as you can see, we use significantly lower energy. We are very good on the CapEx, OpEx, and we don't have any environmental footprint because we are collecting that water that's going waste. So if I go to this example of Cape Town, where there's significant water scarcity, so the current plan is to build a desal plant, but if you went with our approach, we could increase 75% more production, lower the cost of water, because there is actually a 2 gigawatt nuclear plant, about 15 miles from there. So we could pretty much be collecting all that water. And essentially, we estimate that we can, in the next 10 years, can pretty much take over 75% of all the desal market. So this is a team we have assembled. Actually, this person here, Derek, who was a CFO of a big power company, who was advising us in some of these numbers for these competitions, he actually left, he quit and joined us. So we are excited to have him on board. And I want to thank you so much. And I'm grateful for the support that I've gotten here.
All right, thank you very much. We're going to take a few minutes for questions. So does anyone have questions for our panelists on the projects that were presented here, our speed talks? I know, yeah, Steve?
I'm curious what the relative energy impacts are of the electrification, if you will, of the technology. So my question was if you could discuss a little bit what the energy penalty or the energy use component of electrifying the system was.
So as I was showing you, roughly on ballpark, for $1 million savings, our electricity costs to basically charge those droplets is about 10K. So it's extremely energy efficient.
Great. Any other questions? Yes.
The gloves are an example of, the gloves obviously are an example of opportunities that we have to recycle the products on campus. Do the students get involved in the middle step between a recycling goal and who the vendor would be that you recycle with? Because obviously something like gloves has contaminants, all of the things we're trying to get rid of, but you're making a new product, somebody's making a new product out of it. The students at MIT involved in that middle step too?
You mean in selecting the vendor for
In
doing the recycling?
selecting the vendor, getting involved in the, the
yeah.
studies for,
I was not involved in that process, but I have a feeling, and maybe there's someone here who was involved more directly in that, but I think that they were involved in the process, but ultimately because it's EHS that signs the contracts
Right.
and stuff like that, they kind of had the final say. But this whole thing really happened because they really pushed for it, and so
great.
like I said, I think they were involved in that, but just don't know for sure.
I mean, it's just an opportunity. We are the greatest university in the world, so,
Sure.
I mean, we might as well use their abilities.
Sure. Yeah.
So just saying this from the EHS office, there's only a few vendors that do this. So it's really we went with a vendor, and it was all non-contaminated gloves that are going there. So the bio-contaminated gloves would go to bio waste, the chemical contaminated gloves would go to chemical waste still. So it's a subset that's being recycled.
So the 3 million is non-contaminated?
3 million is how many are purchased.
Okay.
There's a much smaller fraction that's actually recycled.
Okay.
And we don't
Okay.
actually have that relative number yet. We might be able to back it out, but yeah.
And also just a quick, I don't know if this is open, but a quick note that it emerged out of the green.
You can put up.
How do you do it?
They'll do it for you.
It emerged out of the Green Labs initiative up front, and so the students were involved. Like, there was one department where one of the efforts came out of the competition that, and the students wanted to do that. So they started the process that became this effort.
All right. Any other questions? I was curious, Rhonda, the life cycle assessment process that you're working on with buildings, could that be applied to LEED certification for new projects? Could you get a point for that?
You can just use yours.
Oh, is it working? Okay. Not yet. I think LEED is still, the slide I was showing before, it still uses two methods. It uses environmental product declarations, which are, they're LCAs of individual products, essentially. And then there's whole building LCA, which covers only the first 3 phases, I would say. But my understanding is Jeremy and team have been talking to USGBC to see if they can start to integrate a more holistic approach to life cycle assessments. And this is one of the ways that they're talking about. Right?
Yeah, I would say it could be used for that whole building LCA, but it would kind of be overkill, right? It would be a quick way to do it, but we're trying to get them to ask more difficult questions. So.
And Kripa, just a quick question about the collaboration, because I got to see some of this happen. It seemed pretty exciting and maybe unlikely partnership at first. Remember that first meeting that we went to? So on one side of the room sat the researchers, and on the other side sat the operation folks. And we threw out the ideas, and something magical really happened. I just thought you could speak a little bit about that, because that's the magic of living labs in many ways.
Yeah, I think the first meeting, we met with a whole bunch of folks from the power plant, but also the facilities. And I think there was a sense of, I think we came together in that meeting, and there was a lot of support from the other side. And we also, while I worked in the power industry before, my students, it was new to them to be in a power plant and so on. So we received a warm reception, and they opened the doors to us and let us be in the power plant and train the students. So I think overall was a great collaboration.
Great, thanks. Any other questions? All right, so we're getting ready to take our first break of the morning, so feel free to take a few minutes to go to the restroom, check your emails. I'd also like to encourage you to visit the apparatus, which is over this way. My friend, colleague Brian is showing the apparatus. So what is the apparatus? This is a device that collects various artifacts from living lab research. So actually, if you go and check things out, you'll see adventure cards over there. The adventure card is a handheld index card, not like sports trading cards that you see for baseball teams, but we've made them for 25 different living lab projects. So the stories of living lab research are told. There's a dot voting activity on the front of the apparatus, so you can let us know if you are aware of a certain research project or not. We even have examples of reports on the apparatus, so if you're so inclined to check out the Pathways Sustainability Leadership by MIT report, there's a copy over there for reference, as well as some very important research on flood vulnerability. And since we had our folks up here talking about gloves, there's even some samples of the gloves that are being recycled. And this I got from Lisa Anderson, who was one of the postdocs involved with this. This represents one pulverized glove, the material that comes from that, and this is what they're testing to see if, well, is this process, more or less sustainable than others that we might try. But if you want to check out these, it's kind of interesting to see how the process is. So thank you again to our panel. Let's give them a round of applause.